Welcome back to the fourth video about the details of RS-485 serial communication. In the previous video, we covered the full-duplex RS-485 bus and how to interleave master and slave messages on such a full-duplex bus to achieve real full-duplex speeds. Card here, link in the description. Today we will talk about protocols that are actually using RS-485 as their physical layer. Enjoy! Let's start with Modbus, shall we? Modbus was initially developed by a company called Modicon in 1979 and was maintained by Modicon until 1997, when Schneider Electric took over and maintained it until 2004. Nowadays, Modbus is maintained by the Modbus organization. What's nice about Modbus is that its documentation is freely available from the Modbus organization, and that's their webpage. Link in the description, where you, amongst other things, find the technical resources with the Modbus specification. And yeah, we have to accept terms, but then we're in. And we'll have some looks into that specification later on. Modbus can use different physical layers. Of course, RS-485, otherwise we wouldn't talk about it. Then RS-232, with some limitations of course, and TCP/IP. Though TCP/IP is not really a physical layer. That would be your Ethernet. Its logical topology allows bidirectional communication between a single master and multiple slaves. It supports the following physical RS-485 topologies: half-duplex or full-duplex, but always with failsafe biasing, respectively, receivers. By the way, the Modbus specification calls failsafe biasing line polarization. Half-duplex is how you should implement a Modbus, and full-duplex is only optional. However, interestingly, Modbus also supports a mixture of full-duplex and half-duplex devices. Let's see how they do that. And for that we will have a look into the Modbus Serial Line Protocol and Implementation Guide version 1.02. Here you find the chapter 3332, compatibility between 4-wire and 2-wire cabling, so full duplex and half duplex. Figure 22 in that chapter shows you how to connect half duplex transceivers to a full duplex system with full duplex transceivers. I've tried to make it a little bit more clear what they are actually doing. So initially you have a full duplex system with a master to slave transmission line and a slave to master transmission line, both of course terminated at both ends. If you want to now connect half-duplex transceivers to your full-duplex system, you simply delete the termination resistors at one end and connect the slaves to master and the master to slaves transmission line, turning it into a single half-duplex transmission line. Yeah, that's it. Two notes here. First, we have now a transmission line that is twice as long as it needs to be. Second, our full duplex transceivers must be able to cope with the fact that they are now receiving their own transmission, either in software or by switching the read-enable pin of their receivers. Since they were designed for a full duplex system, that's not a given. Figure 23 shows you how you can connect full duplex transceivers to a half duplex bus. I've shown you how that works in the previous video, but please note again, these transceivers must now be able to cope with the fact that they are receiving their own transmissions. So the extent of the compatibility between 4-wire full-duplex and 2-wire half-duplex cabling is that as soon as you have a single half-duplex device on your bus, the whole bus falls back to 2-wire half-duplex mode. When it comes to speed, Modbus supports everything between 1200 bauds and 115,200 bauds, at least optionally. By default, all devices communicate at 9,200 bauds, but they must also support 9,600 bauds. Please note, the specification talks here about 56 kilobits per second and here about 115 kilobits per second. That's probably rounding errors or typos. Please note that at 115,200 bauds you can still have a bus length up to 1,000 meters. Consequently, the Modbus specification limits the bus length to a maximum of 1000 meters, with Cat5 cables to 600 meters. Remember, RS-485 specifies a cable impedance of 120 ohms. Cat5 cables have an impedance of, I think, 100 ohms. At the same time, they say they prefer cable impedances greater than 100 ohms. Terminating Modbus transmission lines is a must, but they only give you a maybe value of 150 ohms for the termination resistors. However, they say it's a better choice in conjunction with line polarization, that is fail-safe biasing, to use a 120 ohm resistor in series with a 10 nanofarad capacitor, so an RC termination. When it comes to fail-safe biasing or line polarization, how it's called in the Modbus specification, the resistors have to be between 450 ohms and 650 ohms, and it's noted that using larger resistors may allow you to connect more devices to the bus. The specification also states that with line polarization, 4 devices less can be connected to the bus. A Modbus normally supports a minimum of 32 devices, and if you remember part 1 of the basics, card here, link in the description, an RS-485 bus supports 32 unit loads. If you watch the second video about the details of RS-485, card here, link in the description, you might notice that 4 devices less is quite a low number. So how can they get away with that? The answer is that for terminating the transmission line, they are using 150 ohm resistors instead of 120 ohm ones. That out of the gate significantly reduces the load on the transmitters on the bus. Respectively, the better choice of using an RC termination with line polarization reduces the load on the transmitters even more. In turn, the question arises, how can they get away with using 150 ohm resistors for termination instead of 120 ohm ones? Especially when you consider that the Modbus specification allows you to put the pull-up and pull-down resistors for fail-safe biasing anywhere on the line. That all creates points of impedance mismatch on the transmission line and those reflections. The answer here is that because of the comparatively low speeds, by default 19,200 bauds, they don't care as much about reflections. One more dreary point before we move on to something a bit more interesting, the serial configuration. Modbus has 2 different transmission modes. RTU, which stands for Remote Terminal Unit, you can think of it as binary transmissions, and ASCII, which you can think of as hexadecimal transmissions. In RTU mode, we first have a start bit, which is kinda unavoidable because any standard UART will first send a start bit. Then we have 8 data bits, least significant bit first, most significant bit last. And then we have either even parity, odd parity, or a stop bit, followed by another stop bit. Implementing even parity is required and the default, while implementing here a second stop bit is recommended and odd parity is may. Whatever you do, you always transmitting 11 bits. In ASCII mode, we of course also start with a start bit and then we have 7 data bits. Again, first bit, least significant bit, last bit, most significant bit. And again, we have here the choice between even parity, odd parity, or a stop bit, followed by another stop bit. Regarding the parity and stop bit stuff here, the same rules apply. Note that the transmission here is always 10 bits long. Allowed ASCII characters here, and there are a few exceptions to that as we will see, are the digits 0 to 9 and the capital letters A to F, which means a hexadecimal digit. And please note, you can encode an 8-bit binary value as 2 hexadecimal digits. Yeah, we will come back to that later too. Modbus messages have the following formats. Remote tunnel unit messages, so binary messages, start with a 1-byte slave address, which is followed by a 1-byte function code. After that, you have 0 to 252 bytes of data. The length of the data section depends, of course, on the function code. So you have variable length messages on the bus. At the end, you find a 2-byte cyclic redundant check code. The maximum length of a message is 256 bytes. ASCII messages always start with a colon. That is followed by 2 chars, that is hexadecimal digits, of the slave address. That's nothing else as writing the binary slave address from the RTU message as a 2-digit hexadecimal number. The same holds true for the function code that follows next, and then you have, of course, 0 to 2 times 252 chars of data. Just the binary data from the RTU message written out as hexadecimal digits. That is followed not by the CRC from the RTU written out in hexadecimal digits, but by 2 hexadecimal digits forming a longitudinal redundancy check code. At the end, you have a carriage return character and a new line character. The maximum length of an ASCII message is 513 characters. So, but for the colon at the start and the carriage return and new line at the end, an ASCII message consists just of hexadecimal digits. The addresses used in the messages are organized as follows. Decimal 0, respectively hexadecimal 00, is the broadcast address. It is used by the master to send a message out to all slaves, and the slaves do not respond to a broadcast message. Decimal 1 to 247, respectively hexadecimal 01 to F7, are actual slave addresses used by the master to address a specific slave, and that slave is expected to respond to the master's message. Decimal 248 to 255, respectively hexadecimal F8 to FF, are reserved addresses you should not use. Now let's have a look at the timing of those messages on the bus, and you will see it's very similar to the timing stuff we developed in the The Details video, already carded, link in the description. 3 different cases are shown here in figure 9. The first one is a standard exchange between master and slave. The second one is a broadcast, which we haven't covered in the second the details video. And the third is a timeout or curing. In the first case, the master sends out a message to a slave, and then there is a waiting period. We call that T-reply until the slave replies to the master's message. After the master sends out a broadcast to all slaves, there is of course also a waiting period. We didn't define that in our protocol because we didn't use broadcasts. And if a master sends a request to a slave, but the slave does not answer, we run into, we called it a T timeout. They call it a response timeout. Interestingly, Modbus does not define the exact duration of these timings. In the specification, it just says it depends on your communication speed, on your processing time, etc. However, there is a lower limit for the wait period between messages, here called frames, of 3.5 char. Char being the time you need to transmit a single byte. We call that in our Arduino sketches always T-step microseconds. Interestingly, that timing and the following one is only defined for RTU messages. The second timing gives you an upper limit of 1.5 char for the time between the bytes of a single message. Keeping within that limit shouldn't be a problem when you are using a hardware useout. And that's basically all you need to know to implement Modbus with RS-485 as the physical layer. But you don't have to. On the Modbus page, already linked in the description, you find below technical resources not only the Modbus specifications, but also a lot of offsite links that provide you code and libraries for Modbus implementations. Amongst other things, Simple Modbus, which is a collection of Arduino libraries. Unfortunately, that link here is not really dead, but it hasn't been updated in a while, and there is a more up-to-date forge of those libraries available. It has been created by AngelLog and is called a Simple Modbus Next Generation. It not only supports hardware serial, but also software serial. Link in the description. There is another Arduino library, just called Arduino Modbus, but it's more bloated than the previous one, because it not only supports RS-485, but also Modbus over TCP/IP. You remember, Modbus can use TCP/IP as physical layer. And in addition, it also requires, if you're using RS-485, the Arduino RS-485 library. Anyway, a link to that page also in the description, and the repository for that library is also on GitHub. Also, link in the description. And here's the page for that required Arduino RS-485 library. Another link in the description, and the repository is of course again on GitHub. Last link for now in the description. Let's move on to the heavyweight, PROFIBUS DP. DP stands for Decentralized Periphery. It's maintained by the Profibus and Profinet International, abbreviated PI, and standardized in IEC 61158. There are several parts to that standard, and it has a predecessor, the Profibus FMS, Field Bus Message Specification. On the PI website, link in the description, you can only access meaningful information if you register as a company, respectively if you have a company, yeah, that's what they call it, email address, whatever that means. The IEC standards are of course behind a paywall, and I guess you have to cash out $1,000 or more to get all parts of that standard. There is, however, a document, Profibus Technology and Application, that you can just download from Siemens, link in the description, that contains at least some information. And most of the stuff I'm telling you here I got from that document. You already know that table from Modbus, so let's go through it quickly. But keep in mind that I didn't have access to the IEC standard, so take everything with a grain of salt. Profibus DP supports the following physical layers. Of course, RS-485, that's why we're here, but also RS-485-IS. IS stands for intrinsically safe. That's basically a low power version of RS-485 that you can use in an environment where you have highly flammable or explosive stuff. So it's supposed not to make any sparks. Fiber optics are possible, and MBP, that's the Manchester bus powered, also in the versions low power LP and again intrinsically safe IS. The logical topology is of course bidirectional communication, and here it comes, between multiple masters and multiple slaves. We will have a look at that multiple master stuff later on. The used RS-485 topology is half-duplex with failsafe biasing. Possible RS-485 speeds are up to 1200 meters, 9.6, 19.2, 45.45 and 93.75 kilobits per second. Up to 1000 meters, 187.5 kilobits per second, up to 400 meters, 500 kilobits per second, up to 200 meters, 1500 kilobits per second, and up to 100 meters you can run that thing at 3000, 6000 or even 12,000 kilobits per second. So quite fast. The RS-485 bus length is at most 1200 meters, at least for the lower speeds, and the cable impedance should be between 135 and 165 ohms. That's quite high and much more than the 120 ohms described in the RS-485 standard. Terminating the RS-485 lines is a must, and you have to use 220 ohm resistors for that. Failsafe biasing your RS-485 line is also a must, and it has to be done on both ends with 390 ohm resistors. If you do the calculation for the combined termination resistance at the end of the line from the termination resistor and the failsafe biasing resistors, as we've done in the second part of the details, already carded, link in the description, you end up with about 171 ohms, which is quite close to the 165 ohms here of the line impedance. And it has to be a close match because we want to run the stuff here at 1200 kilobits per second. Oh, and I forgot to mention, of course, it's a maximum of 32 devices on the bus. There's only one valid serial configuration, so start bit, then 8 data bits, least significant bit first, most significant bit last, even parity, and a stop bit. The stuff I'll be telling you now about the Profibus Protocol I got mostly from the Profibus manual. A great resource for detailed technical information about Profibus. Link in the description. Profibus DP knows 1, 2, 3, 4, 5 different message formats, or telegrams like they call it. But for the short confirmation, all these telegrams start with a 2-byte start delimiter, which has a different value for each format. Again, but for the short confirmation, each telegram contains a 1-byte destination address and a 1-byte source address. But for the token telegram and the short confirmation, all other messages contain a 1-byte function code, a 1-byte frame check sequence, and an end delimiter, 2 bytes. The function codes have nothing to do with the application. They are bit fields with 8 flags which contain information used by the protocol itself. The frame check sequence is really just a 1-byte checksum for Telegram. And the end delimiter has a fixed value of hexadecimal 16 for all messages that are using it. The no data telegram has a start delimiter with a value hexadecimal 10 followed by a destination address, a source address, a function code, a frame check sequence, and the end delimiter. It contains absolutely no application data and is used by the protocol, for example, to indicate that a previous message has been received. The variable length data telegram is the first telegram that actually carries some application payload, obviously of variable length. Its start delimiter has a hexadecimal value of 68. Then comes the 1-byte length. We'll come back to that later. In the next byte, the length is just repeated. Then the start delimiter is repeated. It follows the destination address, the source address, the function code, and then 1 to 246 bytes of protocol data unit, or PDU. At the end, we have our frame check sequence and then the end delimiter. The length is the number of bytes in the PDU plus 3. So we are counting the bytes in the PDU plus the function code plus the source address plus the destination address. The application payload is of course here in the protocol data unit. The fixed length telegram is the only other message that contains application data, obviously of fixed length. That is an 8-byte PDU. Its start delimiter has the hexadecimal value A2, which is followed by the destination address, the source address, the function code, and then that 8-byte protocol data unit. At the end, as always, the frame check sequence and the end delimiter. The token telegram is only passed between masters, and it's used to pass control over the bus from master to master. Its start delimiter has the hexadecimal value DC and then follows a destination address, a master, and a source address, also a master. Finally, we have the short confirmation telegram. It's just 2 bytes long and carries a hexadecimal value of E5. It's used in cases where you don't want to use that large no data telegram just to confirm that you've received a message. The 1-byte source and destination addresses have in the most significant bit a protocol-related flag. The 7 least significant bits contain the address, so 0 to 127. 0 is reserved for diagnostics, 1 to 125 are the master and slave addresses. By convention, masters are in the lower address range and slaves are in the upper address range. 126 is for setting device addresses over the bus. Yes, there are Profibus devices that support that. And 127 is the broadcast address. As mentioned before, a master token is passed between the masters to decide which master at one point in time has control over the bus. So for example, master 1 passes a token to master 2, and then over more steps a token is passed to master n, which passes the token back to master 1. It's a daisy chain. Passing the token from one master to another, here for example from master 1 to master 2, takes 3 telegrams. First, master 1 sends over a token telegram to master 2, and then master 2 is confirming that it has received the token telegram by sending back a no data telegram to master 1. And master 1 confirms that it has received the no data telegram by sending over a short confirmation telegram to master 2. Yeah! Now for the timings. First of all, within a transmission, no gaps between bytes are allowed. That's in some cases a tall order. Between transactions, so for example a request from a master and the related response from a slave, there has to be a quiet time on the bus called T-syn or synchronization. And that's 33 T-bit, where T-bit is the time needed to transfer a single bit at a given bus speed. So all the timings here are relative to the bus speed. In the protocol we developed in the second The Details video, already carded, link in the description, we called that time T message min, so the minimum time between a transaction. Before a slave answers to the request of a master, it has to wait at least min T SDR. SDR stands for station delay of responder. And that timing is 11 T-bit. That min T SDR contains TRDY, so a ready time of requester. That's the time the master needs to get ready to be able to process the response from a slave. And that should be below 11 T-bit. It also contains TQUI, the quiet time for modulator. That's between 0 and 9 T-bit, and it's the time the transceiver of the master needs to switch from transmitting to receiving. Min T SDR also contains TRDY, that's the ready time of requester, which should be below 11 T-bit, and that's the time the master needs to get ready to receive and process the response from the slave. And TQUY, the quiet time for modulator. Depending on the bus speed, that's between 0 and 9 T-bit, and that's the time the transceiver hardware of the master needs to switch between transmitting and receiving. In our protocol, we called min T SDR T reply min, and the combination of T ready and TQUY T switch. Max T SDR, depending on the bus speed between 60 and 800 T-bit, is the maximum time in which the slave has to start its response to the request of the master. TSL for slot is depending on the bus speed between 100 and 1000 T-bit, and it's the time in which the slave had to send out the first byte of its response to a request from the master. The difference between the two timings is that max TSDR is intended for the design of slaves, while TSL is used by masters as a timeout if a slave doesn't respond. In our protocol, we just used T timeout max for both purposes. I'd love to say, now you know enough to implement Profibus, but that would be a lie. I glossed over a lot of details. For example, the meaning of the flag in the addresses and the meaning of the 8 flags in the function code. When it comes to existing Arduino code for Profibus DP, there's not much out there. The only thing I could find here on Github was 20, the Arduino Profibus DP. But curb your expectations. That's not a full Profibus DP library. That's a one-trick pony, just sending out a command to some Profibus device and getting feedback. And that's it. But anyway, if you want to have a go at it, link in the description. Last but not least, the cool kid on the block, DMX, which stands for Digital Multiplex. This is not about industrial automation like Profibus or Modbus. This is about stage lighting and effects, for example lasers. How cool is that? It has been developed in 1986 by the United States Institute for Theater Technology, USITT, and was initially called just DMX512. Then in 1990 there was a revision of that standard that was then called DMX512/1990, and finally in 2004 it became an ANSI standard E1.11, also known as DMX512-A. There was a revision in 2008 of that standard, and I think there are more revisions currently in work or have already been published. Fortunately for us, you can download the, superseded version of the standard for free. Here it is, link in the description. It can use the following physical layers: RS-485 of course, USB, wireless. That's not your standard wireless LAN, that's a proprietary technology. And then UDP IP, so also Ethernet. Its logical topology is a unidirectional communication from a master to multiple slaves. So the slaves don't send back messages to the master. That's pretty much an RS-422 multi-drop serial connection, but using RS-485 hardware. Consequently, the RS-485 topology is half-duplex, with the master only using its transmitter and the slaves only using their receivers. The RS-485 speed is fixed at 250 kilobits per second. The maximum RS-485 bus length is 300 meters or 400 meters. It depends which source you are reading. The cable impedance should be 110 ohms or 120 ohms. Funnily enough, both parameters are not defined in the ANSI standard. The ANSI standard is just referring here to the RS-485 standard. Terminating your RS-485 transmission line is a must, and you shall use a 120 ohm resistor. RS-485 failsafe biasing is a may, literally. You may, according to the standard, implement failsafe biasing if that's needed to ensure signal integrity. Yeah. The serial configuration is 1 start bit, of course, then 8 data bits, first the least significant bit, last the most significant bit, and then 2 stop bits. DMX knows only one kind of message, called a package. Byte 1 of that package contains the start code, byte 2 slot 1 data, byte 3 slot 2 data, and so on until byte n+1 with the slot n data. So we can have a maximum of 512 slots, and the total length of the message is at most 513 bytes. The start code is usually 0, which stands for dimmer class data. The start codes 1 to 255 are reserved for future expansions. There is no slave address contained in that package. It's always addressed to all slaves. And by the way, we also don't have a checksum or something. So, how does that work? Let's assume, for example, that we have some left stage RGB lights. Each light is a slave. They all receive the same packages, but the left stage lights are only interested in the slots 1, 2, 3, which contain their RGB values. While the center stage RGB lights, which are also slaves, are just interested in the slots 4, 5 and 6, which contain their RGB values. That's simple. The timing of DMX packages is interesting, to say the least. So before a packet starts, we can have a logical high called mark before break, or MBB, and that should be shorter than 1 second. Note, this can be also 0 seconds long, so non-existent. The mark before break is nothing else than an idle bus state. Then the package starts with a logical low called break, and that should last for at least 92 microseconds. Before the first byte, we have another logical high called mark after break that should last for at least 12 microseconds, but should be shorter than 1 second. Then the bytes follow, at most 513, and you are allowed to have pauses between the bytes, but they should be shorter than 1 second. A whole packet is at least 1204 microseconds long, but should be shorter than 1 second. And the time from break to break is also at least 1204 microseconds and needs to be shorter than 1 second. Remember, the mark before break can be 0 seconds long. The maximum time for break to break and for a packet prevents you from going crazy about pauses between the bytes, the mark after the break and the mark before break. Creating the break requires some creativity when programming. And that's it! Together with the admittedly outdated specification, you should now be able to implement DMX. But again, you don't have to. There are 2 Arduino DMX libraries available. The first here, that's DMX serial from Matthias Hertel. And the repository for that is, of course, on GitHub. Links in the description. The second library is also to be found on GitHub, and it's from Paul Stoffregen, and it's called DMX Simple. Also, link in the description. That's it for today, and at least for now, also for RS-485. I might make another video or 2 in the future, but for now, to be honest, I had enough. Anyway, till next time, bye.